Alright class, so we're going to continue talking about electrochemistry. The last thing that we talked about, we said that we can measure the E cell potential for redox reaction using a voltaic cell. So voltaic cell is used to measure the voltage between two half reaction. Because remember, redox is a transfer of electron. Now, let's go over the voltaic cell in this lecture. I want to build a voltaic cell video. Now, to build a voltaic video, I picked an easy redox reaction. Zinc plus copper plus 2 going to zinc plus and copper solid. So let's consider this. I'm going to build a voltaic cell for this one. Now, how are we going to do that? We are going to have two beakers, okay? I'm going to have two beakers. Here's one beaker over here. And then here's my other beaker over here. And one of my beakers is going to be an oxidation half reaction, and the other one is going to be my reduction half reaction. Now, if you look at the reaction that we're building a voltaic cell for, which one is being oxidized and which one is being reduced? You can see that zinc is being oxidized, right? Because zinc goes from 0 to plus 2. Now, what happens to copper? Copper goes from plus 2 to 0, right? So copper is being reduced because oxidation is loss of electron. You become more positive. Reduction, you become more negative. Okay, so far so good. So that means is that my oxidation was my zinc solid going to zinc plus 2, and I lost 2 electrons. Because remember, oxidation is loss of electron. And my reduction was copper plus 2, gained those 2 electrons, and it got reduced to copper 0. Because reduction is gaining electron. It gained electron. So far so good? Okay. So again, what that means is, over here, I'm going to have a zinc plus solution, and over here I'm going to have a copper plus solution. Now, the next thing that I need electrodes. The next thing that I need electrodes. So what I'm going to have a zinc electrode over here and a copper electrode over here. Okay, so I'm going to use zinc and copper metal. Why am I using zinc and copper metal? Because metals, they conduct electricity, so they can be used as electrode. So this one over here, this is going to be my zinc electrode. And this one over here is my copper electrode. So I'm going to use a zinc and copper metal because they conduct electricity. So far so good? Okay, and they're dipped into their solution. Alright. Now, remember this. We have oxidation, which loses electron. It gives that electron. And reduction, which accepts the electron. Now, oxidation. So this one is my oxidation beaker. And what we call that? We call that anode. And over here in this beaker, this is my reduction reaction, and we call this one cathode. The way I remember it is that anode and cathode, they both have valves. Okay? Again, and then remember, anode, or this is the oxidation, is going to give out electron. The cathode is going to accept the electron. And I'm actually going to write that down because that's very key. So this one is going to gives out electron. This one is going to accept. It accepts electron. Okay. So far so good. Now we have to somehow be able to transfer these electrons between the electrodes. So we know this one is going to give out, this one is going to give out electron, this one is going to accept electron, but we need to somehow allow the transfer of electrons between the two electrodes happening. And the electrons will always go from anode to cathode. It will always go from anode to cathode. So to be able to facilitate the transfer of electron, what we need to connect these guys. We need to connect these guys using a wire. Okay? We need to connect the cathode and anode electrode using a wire to create a circuit, basically. Now, what I'm gonna have a voltmeter. Voltmeter is going to measure my transfer of electron. Okay. Again, oxidation is going to give electron and reduction is going to get it. So electron will always flow from anode to cathode. The electrons will always flow from anode to cathode. The electron will always flow from anode to cathode. So far, so good. Okay. So again, you can see over here that we have a flow of electron from anode to cathode, and then we have a voltmeter that could measure that. There is one last thing we need. Where this one came from? There is one last thing that we need. Let me fix this one. There's one last thing we need, and that is a salt bridge. Okay, so the last piece of thing that we need is a salt bridge. Let's talk about what's a salt bridge before I put it in our voltaic cell. So salt bridge is to provide ions to balance things out. So it provides the ion to balance the charges. Okay, so salt bridge, what does it do? It will provide ions to balance charges. Now, why is that? Here's why. Let's come back over here. You know how over here what's going on is that zinc is turning into zinc plus 2. So what are you going to have? You're going to have a buildup of plus charges on this side. And over here, you're going to have the opposite because copper plus 2 is going to 0. So you're going to have a buildup of negative charges going to. Now, if you have a buildup of charges, what that means is it would stop the flow of electrons. Because here, I'm going to have a buildup of plus charges. If I have a buildup of positive charges, it's going to stop the flow of electron. So what the salt bridge would do, it would prevent the charge buildup. Okay, it would allow the continuous flow. So what it would do, it would allow us to have a continuous flow. It would allow continuous flow of electron from anode to cathode. So basically to balance the charges. All right, we're good so far? Okay, beautiful. So I'm going to put a salt bridge on this one. There are different types of salt bridge you can do. I'm going to use a simple salt bridge. So this is my salt bridge. Now my salt bridge here is basically potassium nitrate. My salt bridge here is my potassium nitrate. Now the potassium nitrate is going to have the nitrate which has a minus charge. So it's going to go here, since on this side I have a buildup of positive charge. And the potassium, which is positively charged, is going to go here since I have a buildup of a negative charge here. So here's my salt bridge. My salt bridge is basically potassium nitrate. Okay. Now, so far so good. Now, I want to kind of go through this with you to see what happens. So pay attention to this part. We're almost there. And right now, here's what happens. I have a zinc metal right here. Now, zinc has a tendency to get oxidized. So what zinc wants to do, zinc wants to lose electron and become zinc plus 2. When zinc loses electron and it becomes zinc plus 2, what does that mean? That means it's going to lose electron, zinc is going to become zinc plus 2, and it's going to jump into the solution. right? Because here I have zinc metal. Zinc metal is going to lose electron and become zinc plus 2. Now, so it's going to become an ion and it's going to jump into a solution. Ions are dissolved in water, right? So it's going to be solid, it's going to lose electron and jump into the solution. When that happens, it's going to lose 2 electrons. Those 2 electrons are going to travel towards the cathode, okay? They're going to travel towards the cathode, and when they get here, then what happens is, when the electrons get here, the copper plus 2 is going to get those electrons and is going to become copper metal. So what happens is they're going to get the electron and they're going to jump onto the electrode because they're going to jump into the solid state, and you can see it as deposit on there. So let's go through this again. So here I have zinc metal. It's going to lose electron, jump into the solution and become zinc plus 2. When it does that, it's going to lose electron. The electrons are going to flow over here. Now when the electron gets here, now copper plus 2 in the solution is going to get those electrons and become copper metal, copper 0. So it jumps onto the electrode because now it jumps into a solid state. And you can see it as a deposit on the electrode. So far so good. So here's what there's going on, a flow of electron. So hopefully this makes sense. Now it's kind of hard to draw this every time, right? It's kind of hard to draw this every time. So because of that, we have a standard cell notation. So you wouldn't have to draw this every time. We call it a line notation. So you wouldn't have to draw this like this every time. So here's the line notation, which makes it so much easier. You're going to have oxidation on the left-hand side. Then you're going to have these 2 lines, which will represent the salt bridge connection. This is a salt bridge connection. And then you're going to have reduction on the left-hand side. That's really key. The reduction will be on the left-hand side. On the right-hand side. I don't know my left and right. And oxidation will be my left-hand side. And the way you do this, you basically have your metal, which is your electrode, okay? And then 1 line, and you have your metal ion, which is basically your solution, and you have to mention your concentration. And then, again, I'm going to have my salt bridge here. Then what I'm going to have my M plus, my solution, and I'm going to have my electrode. This is so much easier than drawing out a voltaic cell every time, okay? Basically, the lines, they represent barrier between different phases, right? These are the barrier between different phases. So, let's do our main reaction that was over here. In that reaction, we had, or can just here we have zinc electrode and zinc plus solution. So what I have here, I have, this is a solvent. I have my zinc electrode, and then I have my zinc plus 2, and then those were all 1 molar solution. I'm going to put a double line, represent a salt bridge. Then on this side, why am I so bad at that? I have my copper plus 2 and copper electrode. Then what I have over here, I have my copper plus 2. It was also 1 molar solution. And I have my copper electrode. So far so good. Okay. Now if I do this, I can run this and I can measure the E cell for this reaction. I can measure the E cell for this reaction. Now, if you can see, the E cell that I measured was under standard condition. Remember what the standard condition means. It means 1 atm, 25 degrees Celsius, and 1 molar. And this is why I had the 1 molar going on here. So far, so good. Okay. All right. Very nice job so far. Now, let's do a practice problem. And actually, let's do a hard practice problem. I feel like you guys got this down. One really quick thing again, before I go to the practice problem, I just want to understand again This is my oxidation, my reduction. The electrons are flowing, and as the electrons flowing, I have a voltmeter. It's going to measure that, and when it does that, I can figure out the E cell for this value in this reaction. All right, so this is a hard problem, but I think we can do it. Let's do it. This is a hard problem. So calculate the voltaic cell for a galvanic cell. What does that mean? It just means voltaic cell. I'm going to use the different word that people use, so when you see it, you won't be confused. Okay, so this is a reaction that goes. Now in this reaction, we have a silver metal, and it involves iron 2 and iron 3. On the exam, I won't make it this confusing, but let's go over this one together. So I have a silver metal, and which silver metal can turn into silver plus 1, and I have an Fe plus 2 and then an Fe plus 3. So there are a few ways we can put this together. We can say that we have silver, okay, and the silver metal can go into silver plus, okay. That's one way we can do this. And then, so what that means is, this is going to get oxidized. And then what that means is, what happened to my iron? That means my iron needs to get reduced. So we have to have Fe plus 2 here, and Fe plus 3 going to Fe plus 2, because then this one would get reduced. Because one has to get reduced, one has to get oxidized. Or, what do you think? How about I can also have silver getting reduced? I can have silver getting reduced, and then I can have iron getting oxidized. Again, I want to mention this one more time. Don't forget this. Oxidation, you become more positive. Reduction, you become more negative. So these are my options, right? These are my options. Now, which one am I going to go with? Because I didn't give you any information. I just said we have iron plus 2 and 3, and then the silver metal. Now you figure it out. These are, I can have silver being oxidized and iron being reduced, or I can have silver being reduced and iron being oxidized. Now here's the thing. Do you have your SRP in front of you? Take out your SRP, okay? Take out your SRP for me. And then if you take out SRP, we are going to add up these values to see what is going on, okay? Let's add up these values. If you look at the silver, so here silver is being oxidized. So go ahead and bring out your SRP first. Here my SRP, and I've already labeled the ones. Here the silver plus going to silver 0, and then Fe plus 3 going to Fe plus 2. Okay? So if I go here, my silver is my oxidation. I'm going to go over here. Now, these are reductions, so I need to flip the sign, right? I need to flip the sign. So this would be negative 0.80 voltage plus, and then Fe is my reduction. So this one would be my reduction over here, 0.77 plus 0.77. You can probably already tell me that this reaction is not going to happen, right? This reaction is not going to happen. It's going to have a negative 0.03 voltage, okay? This reaction is a no-no. Now, over here, again, if my silver is my reduction, so silver is my reduction, which means I can take that number, and that number is 0.80 voltage. Now, my iron is my oxidation, so plus minus 0.77, because I need to flip the sign for oxidation. I get 0.03 voltage. So you could set it up either way, but this reaction will go and this reaction will not go. So that's how I know this reaction down here is the reaction that I am looking for. So far so good? Okay. Again, because again, the question tell you that iron 3, iron 2, and silver metal are the only ones that are involved. Okay, so now we're going to make a line notation for this. So I know my oxidation and I know my reduction. My oxidation is my iron and my reduction is my silver. Because if you remember, we have to do the oxidation on this side and we have to do the reduction on the other side. Now, let's actually do the reduction part. The reduction part is a little bit easier. So I'm going to put the salt bridge here. So I know I have silver +1, standard condition, and I have my silver metal, because silver is going to be my reduction, because silver is my reduction. My oxidation are these two. Now here's the problem. My oxidation is between Fe+2 and Fe+3. What am I going to use for an electrode? These two are both, how am I doing? These two are both solution. They're both ions. They're not metal. So what can I use for my electrode? You guys see the problem? So this was easy. I have silver and silver plus and silver metal. That was pretty easy. So I can set this up. Silver is my electrode. That's going to be on my solution. Now here I have +3 and +2. They both are ions. Only for the oxidation part, I'm only having ion species. So what do? There's no metal. If there's no metal, but I still need an electrode. If I don't have an electrode, the electrons cannot flow. So what we can do, we can choose an inert metal that won't react or complicate things. So we can choose a metal. Inert means there is a metal that is not going to react. It doesn't complicate things. It doesn't do anything to serve as an electrode. And the one that they usually use is platinum. So that's going to be my inert electrode. It doesn't really do anything. It just sits there and it just helps to facilitate transferring of the electron. Again, and that's really key, because I would need a metal that is not going to get reduced or oxidized. And platinum is really good. You guys know what platinum is? Platinum is actually white gold. When you have white gold, you have platinum. So gold, platinum, those are great because they don't get oxidized. That's why they're so expensive. So I'm going to use an inert electrode, because I still need an electrode to make the electrons flow around. So far so good? Okay, and that is going to be our line notation. Nice job. Nice job. Okay, now I want to make you a summary before we do another, actually no, let me do a practice problem. Let's do another practice problem to make sure you got this down. Here is our next practice problem. What I want you to do is calculate the E cell for, now this time I'm actually going to give you the line notation. I'm actually going to give you the line notation. And I'm going to ask you to calculate the E cell. Okay, so I actually gave you the line notation this time. So here's my line notation. I'm asking you to calculate the E cell value. Here's how you would look at this. You go, okay, first of all, this will always be my oxidation on the left. This will always be my reduction. So I know what's my oxidation and I know which one is my reduction. Okay, so my oxidation here is I do have Fe metal. So Fe0 going to Fe+2. In this case, this is what my oxidation is going to go. So I'm going to come here. Do you guys find that? Fe0 going to that right here. Okay, look over here. But it's oxidation, so this sign has to be flipped to 0.44. So this is going to be 0.44 volt. Plus, now my reduction is silver. It's going to be over here. This is my silver. Okay. And I don't do anything because these are all reduction. Just the oxidation needs to be flipped. So plus 0.80 volts. What's going to be end up happening is 1.24 volt. Okay, that's the E cell for this reaction. Will this reaction happen? Yes. Now, what happens if you were add this up and you get a value that is negative? If you have a value that is negative, that means the reaction is not going to happen spontaneously. What do? Switch these two. When you switch these two, then you can flip the sign and now the reaction will go. So if you do a reaction and it doesn't work because it's not ready, you get a negative value, switch the place of oxidation and reduction, and then you can make the value go, and then this will be a spontaneous reaction. Okay, beautiful. Now I'm ready to do a little summary for you. Here's a summary. So remember, if the E cell value is more than 0, is positive, that means the value is spontaneous. If the E cell value is negative, less than 0, that means the value is non-spontaneous. If it's non-spontaneous, what does that mean? That means you need an external power supply to make the reaction go. Okay, it's not just gonna happen. Now, what happens if the E cell is equals 0? That means you are at equilibrium. No work can be done. Also, what that means is you have a dead battery. Because remember, a lot of the redox has to do with batteries. All these reactions are going on. There's voltaic cell inside the battery. So E cell value is positive. That means the reaction will go right here. Okay? Right here. E cell is negative. This is not gonna go. You need to probably switch it out. E cell is 0. The battery is dead. You are at equilibrium. You are at equilibrium. Okay, so far so good. All right, so next time what we're gonna do, we're almost there. We're just gonna keep doing practice problem and talk about one more thing. Now, before I let you go, I'm gonna give you a take-home problem to do. Silver chloride. I have my NaCl 1.0 molar, and then voltaic cell, I have silver nitrate 1.0 molar, and I have my silver metal. Okay, what I want you guys to do, I want you to calculate the E cell value for this reaction. It's a hard reaction. Also, I am I'm sending you guys a more elaborate SRP that you're going to be able to find all of these reactions on it. Okay, nice job. I will see you guys next time.